The preceding lecture covered the statistics used to describe the results from a sample. In this lecture, I'm going to cover the statistics used to assess specific questions that can be framed as hypotheses. Most of these hypotheses are about differences between groups or differences between conditions. Well, the most powerful and straightforward test, I think, is the t-test of proportions. We know that is, we conduct that test by calculating the t observed as p minus pi, that is the sample proportion minus the hypothesized population proportion, divided by the standard error of the mean for proportion, which is the square root of p times q divided by n. So in this case, the pi value is 0.88, so we're presuming that the observed proportion of satisfied customers in the previous study is the true indication of the level of satisfaction. So we're comparing our sample of 0.91 versus that presumed population parameter 0.88. And in the denominator is the square root of p, which is our sample proportion, 0.91, minus q, which is 1 minus p, which is 0.09, divided by 500, which is our sample size, and that equals 2.26. So our t observed value is 2.26. And we compare that with the t critical for alpha 0.05 and 499 degrees of freedom. The degrees of freedom for the t-test is n minus 1. And that value is 1.96. And since the observed t is greater than the critical t value, our interpretation is that the difference is statistically significant. And our conclusion then would be that, yes, satisfaction has increased, and we can be 95% certain that that increase is not due to random error. And in fact, the sample represents something other than the population that was represented by the satisfaction level of 0.88. Well, we can answer that same question, or we can do the same analysis by posing the question slightly differently, and that is to determine whether the observed value of 0.91 falls in a confidence interval constructed around the value of 0.88. We know the expression for the confidence interval for a proportion is p, the observed proportion, plus or minus t times the square root of pq over n. So we plug in the values for the p of 0.88, and we get a confidence interval of 0.88 plus or minus 0.02. And we can interpret this by saying we can be 95% certain then that the true satisfaction proportion lies within the range of 0.88 plus or minus 0.02. So this is the true confidence interval for the population as described in the previous research study. And since 0.91 falls outside that confidence interval, we can be 95% confident that satisfaction has improved, because the observed 0.91 is not does not appear to be from the same population as the previous value of 0.88. And finally, we can answer the question by considering the responses as distributions and conduct a chi-squared test across the distribution in the two categories. So the categories are yes satisfaction, no satisfaction. And what we observed were 91 yeses and 9 nos. And what we expected based on the previous research was 88 yeses and 12 nos. So we calculate the observed minus the expected. It's 3 in each cases. We square those values and get 9. And then we calculate the contribution to chi-square for each cell, which is the observed minus the expected quantity squared divided by the expected frequency. So 9 divided by 91 is 0.1, and 9 divided by 88 is 0.1, and 9 divided by 12 is 0.75. And then we sum those contributions to get a chi-squared observed of 0.85, and we compare that chi-squared observed with the chi-squared critical value from the table for 1 degree of freedom and an alpha 0.05, and get 3.84. And our interpretation then is that satisfaction proportions are not statistically significantly different from expected because the observed value does not exceed the critical value. And our conclusion is that satisfaction did not increase. So we've analyzed these data 3 different ways to answer the same question. The first 2 ways, our conclusion was that satisfaction had increased, but with the chi-square test, our conclusion was that satisfaction had not increased. So why does the chi-square test show something different? Well, it's because the chi-square test is the least powerful. That is, and power in statistics means the ability to identify small effects as statistically significant. The chi-square test treats the measure as a simple dichotomy, yes or no, and it ignores the interval scale aspect of proportions, which the other 2 tests use. Thus, the true measure is not the yes-no responses, it's actually the proportion of people who give those yes-no responses. Problem 4. A restaurant chain has just opened a new outlet and wants to assess its success. The other stores average $1,200 in sales per day. A sample of 30 days sales for the new store shows an average of $1,400 per day with a standard deviation of $212. Is this difference statistically significant at alpha equals 0.10? So essentially the question is the new store selling more than the other stores? And this question can be answered with a t-test of a mean versus a point estimate. And that question is $1,400 greater than $1,200 at alpha equals 0.10? Well, we compute the t observed, the t statistic that we observed from the sample as x bar minus mu divided by the standard error of the mean, s over the square root of n. Our sample mean was 1,400. Mu in this case is considered to be 1,200. And the sample standard deviation was given as 212. And the square root of n is 30. So the observed t has a value of 5.17. We compare that with a t critical value of 1.31. And notice this is a one-tailed test. We're framing the hypothesis as the average sales of the new store being greater than the average sales in the other stores. And so we're ignoring the error component on the low side. So our interpretation is that the difference is statistically significant. The t observed, 5.17, is greater than the t critical of 1.31. And our conclusion that we can be 90% certain that the new store is outperforming the old stores. For this problem, we could also answer the question or frame the question as, is $1,400 within a 90% confidence interval of $1,200? The confidence interval, again, is x bar plus or minus t critical times the standard error of the mean. So x bar is 1,200. So we're constructing now a confidence interval about the population, and we're assuming that 1,200 is the parameter for the population. So 1,200 plus or minus 50.8. And we interpret this as no, $1,400 is not within a 90% confidence interval of 1,200. So the new store is doing better. We're 90% confident that a mean of $1,400 is not from a population with a mean of $1,200.